We recently organized a workshop on eye tracking in virtual and augmented reality at ETRA Conference 2018 together with Tis Pfeiffer from Bielefeld University. And for the hands-on session of the workshop, I prepared a Unity code that shows the basics of gaze interaction in VR. I thought the code might be useful for others, so I'm sharing the example code here. And in this video, I'm going to go through the example and explain how different things work and how you could play with it. In our tutorial, people had the chance to play with different types of eye trackers. We had HTC Vive with Tobii eye tracker, as well as SMI and Pupil Labs. So the main idea was to make a modular program in Unity that lets those that they want to develop gaze interactive games to easily make their games without actually thinking about the type of eye tracker they have. The software is meant to be modular, meaning that you could easily combine different sources of inputs, gaze-based, manual, or head-based, and use those for pointing and confirmation. You could also run the code in emulation mode if you don't have any virtual reality headset or any eye tracker. Then you can move the camera using the arrow keys on the keyboard, and you simulate the gaze point with the mouse cursor. To start, you need to download the code from GitHub. I will put the link in the description. You also need Unity, of course. We have tested the program on Unity 2017.4.3, and it might not be compatible with higher versions of Unity. When you open the project in Unity, it looks like this. By default, it runs in emulation mode, so you could actually run the game, and you shouldn't get any error. And you see that you can move the camera around using the arrow keys, and by moving the mouse on top of the game display, you should be able to see a yellow circle following your cursor. If you want to use Pupil Eye Tracker, you need to have Pupil Service running in the background, and what you need to do in the project, you need to disable mouse gaze object, so and then you enable the Pupil object here, meaning that you tell the software that get the gaze data from the pupil eye tracker, not from the mouse. If you have SMI, again, you need to disable mouse gaze and enable SMI object. If you have Tobii eye tracker, there are two more steps you need to do. If you open the Tobii, you see that there are some missing prefabs. That's because we have removed the Tobii SDK because of the license issues. So all you need to do is to download Tobii SDK Unity, and we used version 1.5. You double click on the Unity package and you import. When the package is added to your project, you see that there will be a Tobii Pro folder here, and now we have the prefabs detected. So these are basically inside the Tobii Pro VR and prefabs. What we have is this VR calibration and VR eye tracker objects inside the Tobii. We already have that. You don't necessarily need the VR gaze trail and VR save data. One extra step that you need to do for Tobii, if you click on Tobii Gaze Combine, you see that one asset is missing, and you could find that code inside the main folder of the project that you have downloaded from GitHub. It's called Race Source Tobii, and you just need to copy this file into Assets, VR Gaze Interaction, Scripts, and paste it here. Now the Tobii module is available. You just need to enable that in the game, and when you run the game now, it receives the gaze data from the Tobii eye tracker. I want to run it in emulation mode, so I disable it and I run mouse gaze again. Now let me show you how the code works in emulation mode. All the scripts that we have for this game, they are inside VR Gaze Interaction scripts. They're all here. There are two codes. One is called rotate camera with keyboard, rotate camera with mouse. We find camera eye, which is inside the camera rig, camera head, camera eye. Here we have those two components, rotate camera with keyboard, which is the default one, and here you could set the speed of the movement. There's a different way of rotating the camera. If I disable this component and enable rotate camera with mouse, you see that now I could rotate the camera by pressing down the left mouse key, and as I move my mouse inside the game display, the camera follows the cursor position. That's a different way of moving the camera in emulation mode. Rotate camera with keyboard is more convenient, so I just stick with this one. The second thing I want to mention is that when you run the game, you see that there are three new objects: gaze for interaction. The second one is called reticle ray for interaction. And if you have the VR device with controllers connected, there will be a third object here, controller ray for interaction. These are the main interaction rays that are used for raycasting, and they are all generated in runtime. I'm going to show you how those rays are generated. Click on mouse gaze and you see that there are two scripts here: ray source mouse and output ray. Ray source mouse generates the gaze ray based on the mouse position, and output ray is a generic component that stores the ray. And in this case, the ray inside the output ray is defined by this component, ray source mouse. So if you click on reticle ray, which is the head center ray, we see the output ray here too, but the ray inside this output ray component is defined by this script, ray source reticle. So on mouse gaze object, I could select inside the output ray component. If I select use this as gaze ray for interaction, this, when I run the game, this output ray component generates the gaze ray for interaction that we saw before. So we have it here. That's why we see the gaze interaction ray when you run the game. For reticle ray, we also have this use this ray, which is the head ray, as reticle ray for interaction. And when you run the game, this will generate the reticle ray for interaction for us. So obviously you can't have multiple objects creating the gaze ray for interaction because we only need one gaze ray for interaction. That's why when you want to use Tobii or any other eye trackers, you need to disable mouse gaze, because we already inside the eye tracker we have another ray that generates the gaze ray for interaction. Right now it's disabled, so it's only mouse gaze that's functional. I run the game again. Gaze ray for interaction object and reticle ray for interaction. These are the main rays that we use for raycasting and for pointing. So if you click on gaze ray for interaction, you see there is a component interaction ray, which we also see on reticle ray here. And inside this component, you see a list of hit objects that they show you the name of all objects that intersect with, for example, with the gaze ray. Now I'm looking at object 1. You see object 1, it appears in the list of hit objects of gaze ray. We have the same thing for reticle ray, and the blue circle that you see in the game display, it indicates the center of the head, and it's the head reticle. Now it's intersecting with object 3, and you see the name of object 3 inside the reticle ray. We are doing more stuff with the ray that we have defined. For example, if you click on mouse gaze, we have an extra object, process gaze, and we have 3 assets here. The first one is process gaze, and this applies a simple filtering on the gaze data. It uses a dispersion saccade detection algorithm, and it smooths the gaze data during the fixations. You can define the window size and saccade threshold in degrees of visual angle here. The second thing is, by the way, I'm applying the same component process gaze on reticle ray just to smooth the head center ray as well, but with a smaller window size, of course. The second component is the ray cast trail, which is used to show the gaze point or reticle point in the field of view of the user. You could decide, it's a particle system. You could define, you could set the number of particles that you want to have, particle size, and here you could set whether you want to show the gaze point at a constant depth from the head center, which you define the depth here, or you could set that to hit depth, which then shows the gaze point at the first intersection point with the scene. The other component, show gaze ray, it basically just shows the gaze ray inside the scene view. I run the game here. You see when I move my gaze, you see this yellow ray indicates the gaze ray, and the blue ray indicates the head reticle. And that's just for debugging purposes, really. Now let me show you how you could use those rays for interaction and how you could define interactive objects. There are two tables in the scene. One is called attention aware, where we have three cubes that they react based on the gaze pointing. When your gaze is inside, when you look at the object, they react immediately without any confirmation. So table attention aware, we have three objects. Object 1, the first cube. The first thing you need to do when you want to make an object interactive is to add collider, of course, because we want to use raycasting. The second thing is to add this gaze interaction generic code from here to the object, and this is a generic script that monitors the current state of the pointing and confirmation. For instance, when I run the game, you see that when I look at the object, the gaze in value gets true. When my gaze is outside, it's false. And we have the same thing for reticle ray as well. Now, the blue ray, the head center is intersecting with the object. You see that the reticle in is in, both gaze and reticle in. Now, the main script is here actually that handles those events. We have one example, point and highlight, that we have assigned this component to object 1. It highlights the object when the gaze is intersecting with the object, or reticle ray or laser ray. So any of those rays that, when any of those rays are intersecting with the object gets highlighted. The second example is interesting. Again, we have gaze interaction generic, and we have dynamic transparency. This dynamic transparency and also the one that I showed you, point and highlight, you could use those as a template and open the code, see how it works. It's very simple. They basically handle those events here. Dynamic transparency is an interesting one. It shows you how you could change the transparency of the object depending on the distance between the gaze ray and the center of the object. I mean, how far the gaze is from the center of the object. So I run the game. So you see, when I look at object 2, it disappears. When I look away from object 2, I see that in my periphery, and somewhere in between, the transparency starts changing. Object 3 it's using point and highlight script again, but here we have set gaze and reticle, meaning that it only reacts when both head center and gaze are inside the object. So you see how you could interact with objects using only pointing. We all know that explicit gaze interaction has its own limitations. One of the well-known problems is Midas touch, where you don't want the object to react immediately when you look at it. So we often need to have an extra confirmation step after pointing that you use for selecting the object. So here in the example, we have added a few confirmation events. Inside the gaze interaction generic, you see the confirmation status. If I open this, I can see the dwell events for gaze ray, laser ray, and reticle ray. Dwell is one of the basic methods that you could use as confirmation, and the way it works is that you look at the object and you fixate on the object for a certain amount of time before it gets selected. For object 1, let's set the dwell duration to 2000 milliseconds. So when I look at the object, you see the dwell progress, it starts counting. When the progress is 1, it triggers the gaze dwell event that you could catch later and use that as confirmation. One thing that you need to consider when using dwell time is that you don't want the dwell progress, you don't want to reset the dwell progress when the gaze goes accidentally outside the object because of noise or small jumps. That's why we have this acceptable frame loss here for dual, that you could set 5 frames, 10 frames, or 20 frames, meaning that if your gaze goes outside the object for less than 5 frames or 10 frames, it's still acceptable, so it doesn't reset the progress. But if you stay outside for longer than this, it resets the dwell time. The other confirmation event is like manual inputs, like mouse left click, right click, or middle click. Also, if you have controller, we have the trigger press that you could use for selection. Also, we have defined a set of head gestures, simple gestures like head down, head up, head right, and head left that you could combine with pointing. I want to show you how you could use those events for interaction. Let's look at the second table in the scene, selecting objects, where we have three cubes again. And for all these three cubes, we have gaze interaction generate component. For object 4, we have this script here, confirm and highlight, where we have defined the pointing to be gaze and confirm with dwell time. So run the game. So when I look at object 4 and do a dwell for 1 second, the object 4 gets selected, as you see here. For object 5, we have the same, we are using the same script, confirm and highlight, but we use gaze. For confirmation, we use mouse left click. So I look at the object and I press the left key and the object gets selected. For object 6, we have gaze for pointing and head down for confirmation. So I look at the object and I do a head down gesture to select the object. Doesn't work in simulation mode properly, but if you have a VR device, it should work properly. So I think that was all I wanted to explain about this example code. Now you see what I meant by modular at the beginning of the video. You actually have different sources of inputs, manual, gaze-based, head-based, that you could combine together differently and build your gaze interaction by combining those pointing and confirmation events. I hope you find this code useful. If you have any question, please feel free to write down in the comments below. And remember, if you want to distribute the code, make sure that you remove the Tobii SDK from the project.